All right, last time we started parametric equations. Today we're going to move forward a little bit with parametric equations in the real world settings. So up on top here, it tells us parametric equations are often used to model projectile motion. Because projectile motion has both a horizontal and a vertical component that are independent of each other. And so they've shown us our two equations here. For the horizontal distance, we've got x equals v naught, which is the initial velocity, times the cosine of theta, which is going to be our angle, and then times t. For our vertical component, they've got v naught times sine of theta times t minus 16t squared. Now I'm going to show you a different form of that equation just so you have all of them. That equation we'll see a lot of times as -1/2 times g times t squared plus v naught times sine of theta times t plus h naught. So they've simplified it a little bit to get to this point, but I wanted you to see where it comes from. This is -1/2 times the pull of gravity. Here we do feet a lot of the time, so that's -32. So that pull of gravity is equal to -32. If you're working with meters, then it would be the 4.9. That's what our difference is going to be. So they went ahead and multiplied that -1/2 times the -30 times the 32. Sorry, I don't know why I wrote that negative there. Times the 32 to get that -16t squared. That's where that's coming from. The other piece that you see missing there is this plus h naught at the bottom. This is the initial height. And so the problems that we're about to deal with don't have a height since they're taking off the ground. But I did want you to see where that is all coming from. Again, the v naught is the initial velocity of the object. And then our v naught is our initial velocity. H naught is our initial height. So we're going to write a parametric equation for the path of a cannonball shot from a cannon with an initial velocity of 87 feet per second and an angle of elevation of 60 degrees. So we're going to start our equation for x of t. And so that is our horizontal here. And that tells us v naught times cosine of theta times t. And so our v naught here, our initial velocity is 87. So we get 87 times the cosine of our elevation of 60 degrees times t. Now, if you remember your unit circle, you can go ahead and simplify that because the cosine of 60 is 1/2. And then if you multiply 87 times 1/2, we get 43.5t. So that would be the most simplified form of that equation. Our v naught was 87, our theta was 60 degrees, and that h naught was 0 because it's coming from the ground. So our initial height is 0. All right, so then for our y2, that puts us at -16t squared plus 87, which is our initial height, our initial velocity, times the sine of 60 degrees times t, plus our 0, since the initial height is 0. That too will simplify, so we end up with -16t squared, plus that 43.5 times √3 of t. And again, that's coming from the sine of 60 is √3/2. And so when that simplifies, we get 43.5 √3 times t. All right, the next part here says to sketch the graph of this equation. And so we're going to go from the ground here at 0, 0, and this ball is going to go up. The cannonball is going to go up in the air and hit back at the ground right there. So there is the sketch of our graph, and we'll come back to that a little bit and label some more as we answer some more questions. So it says approximately when the cannonball hits the ground again. If it was back on the ground right here, its height would be 0. So I can go ahead and use our vertical component, which is this v of t, to find that time when it is back at 0. So I'm going to plug in 0 for our final height there. And we get negative 16t squared plus 43.5 root 3 t. Now we're solving for this t here. This is one that we can factor a t out since both of these have a t in them. So I can solve this by factoring. I get t times negative 16t plus 43.5 root 3. Now the first t here is going to give us 0. So remember when we factor and we've got this, we set each one of them equal to 0. Well, that one's easy. That's where it took off. So our time was 0 when it took off right here. The one we're looking for this is this part. So I can take my second factor here and I could set it equal to 0. So I get negative 16t plus 43.5 root 3 is equal to 0. I'm going to go ahead and add that 16t to get it to the other side. So I get 43.5 root 3 is equal to 16t. And my last step is to divide by 16. This is just something I would put into the calculator to find. And so we get 4.7 seconds. So that means that when it goes back on the ground here, that would be at 4.7 seconds. It's back on the ground. All right, the next part says, if there was a 30-foot wall 190 feet from the cannon, would the cannonball clear the wall? So we want to think through this. The first thing we want to see is, will it get enough horizontal distance? Because the wall is 190 feet from the cannon. So we want to know if it went at least to the 190 feet so that it could get past that wall. And so we can know that by plugging in our time here. So our vertical was x equals 43.5 times the time. And we know it took 4.7 seconds to get back on the ground. So we want to see how far it went there. Again, this is one that you can plug into the calculator. So you would get 43.5 times that 4.7, which is 204.84 feet. So our horizontal distance, that point right there, is 204.840. So it did go far enough because 204.84 is past the 190. So it does go far enough to the right or in the horizontal. Now we need to know, did it get high enough to pass that 30 feet? So we want to know at 190 feet, how high is it off the ground? So we are going to plug in the 190 for our horizontal. So that we can see what the time is, and we can use the other equation to find its vertical there. So I divide by 43.5, and we find that the time is 4.37 seconds. That is when it has arrived at the wall. So the ball has traveled 190 feet at that point in the horizontal. It has taken 4.37 seconds. So we can use that to figure out how high it is now by using our vertical component. So y is equal to negative 16 times 4.37 squared. All I'm doing is plugging in that time into this vertical component right here. Plus 43.5 root 3 times 4.37. Kind of ran out of space there. All of this is just computation, so we can put that into the calculator and we get y is equal to 23.84 feet. That means when the cannonball was shot from the ground here and it went to 190, that height there was 23.84. Well, the wall is 30 feet, so it was unable to clear that. There's not enough height on the cannonball at that time. So the cannonball would not go over that wall. All right, the last question says, what if there was a 35-foot wall 180 feet from the cannon? So this is a different scenario. We're looking at 180 feet from the wall. So we do that same process again. So if you want to pause, try this one on your own and check it. So 180 feet from the wall, I need to check where that is horizontally. So I put 180 for my X value, and that is 43.5 times T. I'm going to divide by 43.5. And I get that the time there would be at 4.14 seconds. And try not to round till the end on these, even if you're just writing the 2 decimals on your paper and then continuing to use the extended one in the calculator, it gives you more accurate information. All right, so 4.14 seconds in, I know I'm at 180 on the horizontal distance. Now I need to see if that vertical is high enough to clear that 35. So I'm going to take my vertical component and do -16 times 4.14 squared plus 43.5 root 3 times 4.14. So all I've done is plug it into this vertical component. I'm plugging in the time of when it was at the 190. I plug that into the calculator and we get that it is 37.81 feet at that point. That is higher than the 35 feet of the wall, so it could get over. So yes, it will clear. That is higher than the wall. So with the word problems, you're really going to want to think through what is it asking? And am I using the horizontal distance or the vertical distance or the time on this problem? Because there are several components with those parameters in there. All right. So here is another question, very similar to that one. It says, assume that Phil Mickelson hits a golf ball with a velocity of 146.7 feet per second using his 10-degree lofted driver. Also assume that there is no friction, no backspin, and it's a perfect on-center hit. Write a parametric equation for the path of the golf ball. So again, we're doing the same thing. It's a golf ball, so it's coming from the floor. So our initial height would be 0. Our initial velocity, so V naught is going to be 146.7. Our angle here is 10 degrees. And so let's write those equations. So for our horizontal, we do our initial velocity, 146.7, times the cosine of 10 degrees times our time. That's going to give us the horizontal distance of the golf ball. For our vertical, we get the pull of gravity, so that's -16 t squared, plus our initial velocity times the sine of our angle, which is 10 degrees times t, and then that would be plus 0 because of the initial height. I'm going to go ahead and simplify those just so that as we're working, they're easier to work with. When I put this in the calculator, remember when you're putting a degree in the calculator, you want to be on mode and in the degree mode. So I get 146.7 times the cosine of 10 gives us 144.47 t. For this one here, I'm going to plug in 146.7 times sine of t, and we get 25.47 t. And I don't have to put the plus 0 because that doesn't change our equation. Now we're ready to start answering some of these questions. So this next one says sketch a graph of this equation in parametric mode, label the starting point, the highest point, and where the ball lands. So I'm going to start with my sketch. Again, it's a golf ball, so it's going to go up in the air and then come back down and hit here. The direction, so with our parametrics, we want to go ahead and draw our arrow. That is the arrow of our golf ball. Before I start to label this, I am going to go through and answer some of the questions because that's going to help me fill in the labels for this graph. So it says, how far horizontally does he hit the ball, not including any roll time? What is the hang time, which is the total time the ball is in the air? I feel if I answer that, it'll make it easier for me to label some of the stuff on this graph. So the hang time is the one that we're going to want to find first. That's how long it took to get back on the ground here. Our vertical distance here is 0. It is on the ground, so it's going to be at 0. So I set 0 equal to negative 16t squared plus 25.47t. Again, since it's just these two terms, we can factor out our greatest common factor, which is t. So we've got t equals 0. That's our first one. T equals 0 is going to be right here. That's before we hit the ball. And then to find our second one, we take this and we set it equal to 0. So we get negative 16t plus 25.47 equals 0. 25.47 equals 16t. And we divide by 16. We get t is equal to 1.59 seconds. This right here would be considered the hang time, how long it was in the air. So right here, we would be at t equals 1.59. Now, if we want to know how far that made it horizontally, then we need to plug that into our horizontal equation. And so we get x equals 144.47 times 1.59. So I've taken my horizontal component here and I've plugged in the time that I just found that it was the entire time it was up in the air. So that gives me a horizontal distance of 230.02 feet. All right, so I can now label this point right here. That would be at 230.02 and 0 would be the height there. So that's that point right there. All right. So now we've got a lot of information on here. We know how far it went, how long it was up in the air. So we've been able to label several of these points. It does also ask what is the highest point and where. The highest point would be this one right here. There's a couple different ways you can get that. Since this is symmetrical, you can take this t value and divide it by 2, and it would give you the time that it would be there. That's probably the easiest way. So we can take 1.59 and divide that by 2, and we get 0.8 seconds. The other option, you can always do that negative b over 2a on your vertical one, because that's going to give you your axis of symmetry there, or the x value of that vertex. So that was another option, but this is definitely the easiest. We knew it took 1.59 seconds, so halfway through it's going to be at the top. And so now we can find our horizontal and our vertical from that so that we can label that point. So we get 144.47 times 0.8 seconds. And so that gives us 115.01. That's going to be our horizontal distance. To find the y, we plug in that 0.8 into our equation. So we get negative 16 times 0.8 squared plus 25.47 times 0.8. And so that vertical height is going to be 10.14 feet. So this point right here, which occurred at 0.8 seconds, would have a horizontal distance of 115.01 and a vertical of 10.14. And again, that happened at t equals 0.8. So lots of information there, lots of different questions that they can be asking about these real world problems. So you want to make sure that you practice them. There's a very similar problem to that right below it. So if you will go ahead and try that one, see if you can answer those same types of questions. If you want to pause the video, try it, and then I'll put the answers up so you can check that. All right, so in this case, what they've changed is our angle here. So our equation would be 146.7 since it did not change the initial velocity, times the cosine of 45 degrees. For our y of t, it would still be negative 16t squared plus 146.7. Again, here is where we change that. It would be the sine of 45 degrees times t. When we put that in the calculator, that does simplify to 103.73 t. Here we get negative 16t squared plus 103.7 t. All right, finish that up. See if you can come up with those answers. All right, check your work. You should have found that the maximum that it went horizontally was 672.17, and that it was in the air for 6.48 seconds. That allow you to divide it by 2 so that you can find that the maximum height occurred when it was 336.09 horizontally and 168.03 vertically. So that is a good example of a problem that you would have in the real world using these parametric equations. We are going to try another one so that you guys can see another example. So here is one more word problem. It says the left field wall at Fenway Park is 395 feet from the home plate. The wall itself, affectionately named the Green Monster, is 80 feet high. A batted ball must clear the wall to be a home run. Suppose a ball leaves the bat 3 feet off the ground at an angle of 45 degrees with velocity 125 feet per second. So the first thing we want to do is write the parametric equations for that. So I'm going to start with that part, and I'll start with the horizontal. It's a little bit easier to write. And so x is equal to our initial velocity. We should probably name those. So our initial velocity was 125 feet per second. It told us our angle here is 45 degrees. So that's the one that we're going to use. And our initial height is 3. So as we write the equations, we're going to go back to those values. So here we have 125 cosine of 45 degrees times time. Now we simplify. Of course, you know that unit circle, so you know that's root 2 over 2. And we put that in the calculator just to get it easier to work with, and that is 89.3 t, 88.39 t. All right, now we're going to write our y equation. And so that's going to stay as negative 16t squared, because that's negative 1/2 times 32, which is the pull of gravity, plus our initial velocity, which we said was 125, times the sine of 45 degrees, because that's our angle, times time, plus our 3. We're going to go ahead and take that to decimal values as well. You know that sine of 45 is root 2 over 2. We'll go ahead and put it in the calculator so we have numbers that are easier to work with as we come up with the answers here. So that would be 88.39 t plus 3. So our parametric equation is written as these two. This is going to give me the horizontal. This is going to give me the vertical at all our time t's. All right, so it's got a couple different questions here, and I like to kind of go in a different order. It says, what is the maximum height of the ball? How far is the ball from home plate at its maximum height? And if the ball is, we'll get to that one last. So we want to go through these two first. And so what is the maximum height of the ball? That we would want to find is going to be that vertex point. So the first thing I'm going to do is figure out how long was the ball in the air in the first place, because that's going to help me do that half one. And so we want to find when our vertical distance is 0. So I'm going to plug in 0 into our vertical component here. Now in this case, you can't really factor this one because it's got the 3 terms. So you're going to have to come up with another option. Since you guys know quadratics, you know there's a couple different options in solving. Factoring is one of them, but you also have the quadratic formula, and you can also graph and use the graph to figure that out. And that's going to be the easiest thing to do here. And we're going to do it on the calculator. So you can plug this part into y1 and this part into y2 and find the intersection. So let's do that, and I'll do it on the calculator so that you can see it. So in my y1 there, I've put in my right side of the equation, and in y2 I have put the 0. Now when I hit graph, the part that I care about again is this part where it hits the floor. So I'm looking for that. I hit second, trace, intersect. Notice that our calculator is asking me about the quadratic. It's asking me, is that one of the lines that you want to see the intersection on? So I hit enter for yes. Then it says, is the second one y equals 0, which is this line right here? And so I answer yes for that as well. And then it says, do you want me to guess? Guess and question mark? Then yes, I want the calculator to guess. And so there is our answer right there at 5.558. So T would be equal to 5.558 seconds. Now, that doesn't really answer the question that's being asked there, but I need to do that in order to answer the question, because the question is, what is the maximum height of the ball? Well, I have found when the ball is back on the ground, but we know that it reaches its maximum height at half of that time. So I take this 5.558 and I divide by 2. And so that gives me 2.779 seconds. So that is when it's going to reach its maximum height. Still not answering the question yet. These are steps I'm going to have to take to answer the question. So this is when it's back on the ground. This is halfway where it reaches our maximum height. Now, when we're talking about height, we're talking about the y component or the vertical one. So I'm going to plug it into that equation. So I get y equals -16 times 2.779 squared plus 88.39 times 2.779, and I'm sorry about that, I ran a space there, plus 3. And so now we can put that into the calculator and we get 125.07 feet. We finally answered the question for this one. It got to a maximum height of 125.07 feet, and that occurred at 2.779 seconds. Now it says, how far is the ball from home plate at its maximum height? Well, we know the time for that maximum height, and it wants to know how far, so that's our horizontal distance. So I'm going to plug in that time into our horizontal one. So we get x equals 88.39 times 2.779. That's something I can just put into the calculator, and we get 245.64 feet. So that's how far it would be from home plate, because that's my horizontal distance. Make sure you keep in mind that when it's looking for that horizontal, you want to use the horizontal component. When you're looking for height, the vertical, then you're going to use the vertical component. All right, and then they can make you really think like this one right here. It says, if the ball is hit straight down the left field wall, will it clear the green monster? If it does, by how much does it clear the wall? Show all the work. All right, so we want to know if it's going to clear this wall. So the first thing I'm going to do is, we already know how long it was in the air altogether. That was 5.558 seconds. So I can figure out how far it went by doing that. That's the easiest one to check. If it didn't go far enough, then you know it didn't clear it. So I'm going to do 5.558. And so that is 491.27 feet. That is past that 395 feet. So it does have enough horizontal to pass the wall. But we have not finished there. We need to check to see if it has enough vertical. So I'm going to take that 395, which is where the wall is. And so we want to know what the time is when it's that far from home plate. So I put that equal to 88.39, and I'm going to solve for that t. So I put this in for my horizontal, 395, and that's because it says that the wall is 395 feet from home plate. So that's my horizontal distance. And I want to solve for time there to see when it is there. And so we get 4.47 seconds. So at 4.47 seconds, it is 395 feet from home plate. So that's at the wall. I need to check to see if it's got enough vertical to get past that 80 feet. So that's where we use our vertical component. And I plug in that time. I'm going to run out of space again. And so we get 78.41 feet. Now it says the green monster, or our wall there, is 80 feet high. Well, if the ball is only at 78.41 feet in vertical, then it does not have enough height. It's going to hit the wall. So when t is equal to 4.47 seconds, the ball will be 78.41 feet high and will hit the green monster. It will not clear it, so we do not have a home run. That's some real world problems with parametrics. On our next video, we will go ahead and do converting these from rectangular equations to parametrics and back and forth.